Hey guys, welcome to the channel CodeChef. If you want to learn competitive programming and get a good hold on DSA, this is the one-stop destination for you. Every week there are several videos which will enhance your skills in DSA as well as the editorial videos for the CodeChef contest. So if you're new to the channel, then do subscribe to the channel and turn on the bell notification. Myself, Chirayu Jain, I'm a CodeChef educator, and in today's video we're going to discuss about the Prim'sAlgorithm code. This video is a part of minimum spanning trees playlist. Okay guys, so now let us start the discussion of the Prim'sAlgorithm code. So here we will see two approaches, right? One is the approach which will do all of the things in order of n square time, and the other one which is somewhere efficient than this approach, right? So we'll discuss both of them. Okay, so now first let us start with the naive approach, or we can say the brute force approach that we will do to make Prim'sAlgorithm working, right? So first of all, what we're trying to do here is we'll enter the number of edges, and for each edges, right, what is the corresponding edge starting index, ending index, and the weight associated, right? So as we did earlier, but here we are also taking the vertices that are there in the graph, right? So we'll make an adjacency list, right, to store like what edge is associated with what weight, right? So here at a minus 1, because we are inputting all the values, so we are making a zero based indexing over here. So I am putting it in the a minus 1, and the ending index is b minus 1 with the weight w, right? So this is a typical thing how we should make a graph, right? So if you have not watched like what is the basics of graph, you can also watch that in this channel. So this is how we typically make an adjacency list for the graph, and we are making a pair. We are making a pair for the starting index as a minus 1 with the ending index as b minus 1 and the weight associated with that edge, right? So since it is an undirected graph, so we are making for both the things, like from a to b and from b to a as well, we are making the entry in this particular adjacency list. Now, as we have discussed in the approach, that what three things that we should take while making this algorithm run is, first is the weight array, the second one is the parent array, and the third one is the MST node, right, which will tell us that whether this particular vertex is the part of MST or not. So what is the length of these? That is v, which is the number of vertices that we have. Now the initialization part for all of these is, we will initialize the weight array with the int maximum value, right? Why? Because we need to again and again compare with the weight, and the best weight we need to keep it here. The parent array will initialize it with minus 1, because initially all the nodes are isolated and then we are making them into the MST. The third one, MST node array, we should initialize it with false. Why? Because as of now there is no particular vertex which is the part of MST, right? Now let's start with the vertex 0. So like initially we are starting off with the vertex 0. You can take any of the vertex, but let's, for the simplicity, we'll make that we are starting from the vertex 0, right? So what we will do first, we'll initialize the weight of this vertex with 0, because this is the minimum weight amongst all. So we can initialize with it with 0 and start off with this, right? Okay. Now, as we have discussed, right, for a minimum spanning tree, how many edges will be there in the MST, right? There will be n minus 1 edges, where n denotes the number of vertices. So what is the value that we have taken for the vertices here? That is v, right? So how many edges will be there in the final MST? That is v minus 1. So we'll run a loop from I equals to 0 till I less than v minus 1 and I plus plus. And first of all, remember this step by step, that what we do in the Prim'sAlgorithm is, first thing is to find what is the minimum weight as present in the weight array as of now, right? So that part we need to do. So what we can do is, first of all, we'll make an index u and one variable mini, which we'll initialize with int max. This mini keeps the track of minimum weight till the present index that we are traversing on, and it will give us the minimum weight as of now. Okay, and in this u, what we'll try to do, we'll try to get the index of the minimum weight which is present in the whole array, right? So what we will do, we'll run a loop from j equals to 0 till j less than v, that means for all the vertices, and we'll see two conditions over here. Condition number 1 is that this node is not included in the MST, first condition. So MST node of j is equal to false, and the weight of this particular node is less than the minimum as we have traversed till now, right? So it should be minimum, it should be less than this particular mini. So if both the conditions hold true, then what we will do, we'll update the mini, because there is a lesser weight which we have found out. And what we will do, we'll update this variable u with j, because this is the, as of now, the minimum weight vertex, right? That part is done. So after traversing all the vertices, we'll find one u which has the minimum weight, and what we will do, since we have found it, so we will include it in the MST. So what we will do, we'll mark it as that this particular vertex is included in the MST. So MST node of u is equal to true, right? That is done. Now what is the remaining part? Now the remaining part is, we will update the weight in the parent array by traversing all the adjacent node of this particular node, right? Because this is the now the part of MST. So what we will do, we will make a loop for all the adjacent vertex associated with this, right? So with this, in the adjacency list, we have all the pairs which are associated with this particular vertex. So what we will do, we will check that if the weight of this particular vertex, right, if the weight of this particular vertex that we are traversing, right, the neighbor of this thing that we have marked in the MST, right, if the weight of this vertex is greater than the index that we have, right? So what are we storing in this pair, right? What are we storing in this pair? So a dot first denotes the index value and a dot second denotes the weight value, right? So at this particular index, right, the current weight that we have for this, is smaller than this weight at a dot first, right? This weight at a dot first, and also it is not the part of the MST, right? It is not the part of the MST. Then what we will do, we will update first the weight of a dot first, right? We will update what is the weight of a dot first, then we will mark that, okay, the parent of a dot first will be now u. The parent of a dot first will be now u. So this is what we are trying to do over here. Hope you get it. So I'll repeat it once more so that it will be clear. So we will traverse all the adjacent nodes, right, the neighbor nodes of this vertex that we have included in the MST, right? And for all the neighbor nodes, what we will do, the neighbor node is in the form of a pair, right? The first part denotes the vertex which is carried out, right, from this particular u vertex, and the second part is the weight associated between that edge, right, the weight which is having, right? So if at the weight of this first node, right, if the vertex weight is greater, right, the current weight of the vertex is greater than what we have for this current edge, right? Suppose that we are connecting 1 and 2, right? So at the 2 vertex there is some weight which is 50, right, and in this vertex 1 and 2 we have a weight which is 30. So what we will do, we'll update the vertex weight of 2 from 50 to 30, right? So that is what we are trying to do here. And also we need to check that whether this vertex 2 is a part of MST or not. If it is the part of MST, then we'll do nothing, right, because that is already included. If it is not the part of MST, then what we will do, we will update the weight of this vertex because we got a lesser weight, right? And then we'll make that, okay, we have updated this weight and the parent is also updated because of this edge only the weight got reduced, right? So the parent of this vertex will now be u, right, because this is for this only we are traversing all the neighbors. So I hope this portion is very clear to you. Now what we will do, we'll initialize the sum variable with 0 because we need to calculate what is the sum associated with this MST. We have now done with the MST, right? So similarly what we will do, we need to traverse the parent array as we have discussed in the example also. So what we will do, we'll travel it from 1 till v to get all the edges that are included in the MST, and we'll sum all the weights, and we will sum all the weights in this sum variable and we'll output it. So if you run this code, right, then we'll see all the starting and the ending index of the vertices. It can be in any order, right, because it is an undirected graph, and the weight which is associated with the minimum spanning tree, right? So this is the approach, and you can see the time complexity of this approach is order of n square because we are running 2 loops over here. And also it is very important to note here that whenever we traverse all the adjacent things for a particular vertex, right, all the neighbors of it, so the time complexity will be the order of vertices plus the edges that we have. So it does not make the square polynomial time complexity, right? So here only we are getting that it is a order of n square time complexity. Can we reduce this, right? Can we reduce this time complexity? So focus on this particular part, how we can reduce it, right? So what we're trying to get over here is that we are just trying to get that what is the minimum weight in that particular vertex set of vertices, set of weight vertices that we have, right? Only that portion we are trying to get. Just for that only we are making the time complexity order of n square here. Can we reduce this with the help of some data structure? Yes, we do have a data structure which can reduce this. That is the priority queue, which is in turn a part of a heap data structure, right? So in C++, what we try to do is we try to construct a priority queue, so that what we can do is we can get either the greater value from the set of values or the minimum value from the set of values, right? So here we require the minimum value, right? So we use that priority queue which give us minimum value every time when we go over it, we'll get a minimum value, right? So like more precisely I would say that it is a form of min heap that we're trying to construct over here, right? So rest all the code remains same. What we just try to do here is that instead of traversing that particular array, again what we try to do is we construct the priority queue, right? This is a min heap priority queue which we'll name as pq, right? So it consumes a pair of the pair of vertices that consist of the index and the weight which is associated with that edge, right? So rest all the things remain same. What we will do while this priority queue is not empty, right? How we are getting it is we are taking the top of that priority queue. We are taking the top of that priority queue, and the second portion denotes the index, right? The first will denote the weight which is associated. Now second will denote the index. So when we get the index, right? So we'll take it into the variable and pop that value out because that is now taken, right? And we'll mark that this particular value, this uth value is taken and it is the part of the MST now. So we'll mark it as true, right? So this is the portion that we're trying to do here, right? The minimum value we're trying to extract and taking the index of it, right? So we have already taken the index with this priority queue and we'll remove that value, right? Now one slight change also occurs here when we are trying to explore the neighbors, right? When we're trying to explore the neighbors, then what we should do, we should add the value in this priority queue. So what we will do, we'll add the weight first and then the index associated with this particular weight, right, with this particular edge. So this is the small moderation that we do, and the change in the time complexity is that we have reduced the time complexity from n square to n log n, because in log n it will give us the results, right? So whenever we are trying to search for the minimum weight, we have used the priority queue to work it more efficiently, right? And this portion will give us the results in order of v plus c, that is vertices plus edges, right? So at last we'll output this and you will find that the results will be same, right? The results will be same. Yeah, so the results are same over here. We are getting the exact minimum value, that is 150 for the given graph. So this is more or less the explanation of the code in C++ for the Prim's algorithm. I hope that you try this code on your own, and wherever you find the difficulties, you can mention it in the comment section below. I'll look for it and try to resolve it, and let's have a conversation in the comment section also, so that we can discuss, we can see multiple approaches for a given algorithm as well.